for it. And so let's do share screen, the usual routine. All right. All right, let's center this, enlarge it, let's focus it. Okay. Yeah, so I just got a couple of minutes here before it's official time to start. Let me go over some of the stuff we did last time as a review. This was really just the beginning of time-dependent perturbation theory. So the setup is you've got an unperturbed Hamiltonian and a perturbation, which is allowed to depend on time, although in many of the applications, it turns out it won't, it will not do so. The kind of objects one is interested in are transition amplitudes. This is the exact time evolution operator in the middle U of t, which means it's the evolution from h, which is the total of the whole Hamiltonian. And I and f are initial and final states. So this gives you the probability, the probability amplitude to find yourself in the final state f, given that you're in the initial state I at time 0. Oftentimes in this transition amplitude, the initial and final states are actually energy eigenstates of the unperturbed system. That's how it is, for example, in this case of the impulse delivered to the iron atom on the harmonic oscillator. One wants to know the transition between the harmonic oscillator states before and after the perturbation is applied. But in other cases, the initial and final states are kind of limits, perhaps subtle limits of eigenstates of the unperturbed Hamiltonian, as happens, for example, in scattering theory. In any case, there's possibilities for the interpretation of the transition amplitude. We set up two types of time evolution operators, U0 and U. U0 is a time evolution operator for the unperturbed system, which we assume we understand very well. And then the U involves the whole thing, including the perturbation, which is going to be the hard part. So these are the standard Schrodinger equations for the two types of time evolution operators. In the case of U0, you can write it as an exponential. You can do the same thing with capital U also if it should turn out that H1 is independent of time. Sometimes it's useful to do that. And then I think at the beginning of the hour, at the end of the hour last time, I had just explained the interaction picture, basic philosophy of it, which is to strip off the time evolution due to U0 or H0, using U0 to do the job. That's what you see here. And this is a variation on the Heisenberg picture where one strips off the entire evolution. Here you just take care of the part of it that you know how to handle, the unperturbed part. This presumably leaves behind, this then defines the state vector in the interaction picture. This is in the Schrodinger picture. The S subscript means Schrodinger and I means interaction picture. If I leave a subscript off, the Schrodinger picture will be implied. That'll be the default. But in any case, this is the stripping off of the unperturbed evolution. So if we think of H1 as being small in some sense, or localized in time or localized in space, which is the usual situation, one of those choices, then the evolution is dominated by H0. And by stripping that off, we now have psi in the interaction picture evolving more slowly than it did in the Schrodinger picture. Likewise, we define operators in the interaction picture by conjugating by the U0. Okay, I think that takes us up to where I left off last time. Are there any questions about that before we get started on new material? It's just really the beginning of the formalism. Okay, I'd like to begin then with some elaboration on the interaction picture and to say some things about it. So let's see. In the first place, let me draw a line here. So in the first place, let's write the state vector in the interaction picture as a function of time, and write it as a time evolution operator, which I'll call W of t, acting on the state vector in the interaction picture at the initial time. In other words, let's define W of t to be the time evolution operator in the interaction picture. So W is the same sort of a beast as the U0 and the U, which are also time evolution operators. by the way, I didn't mention this, but at t equals 0, if I substitute t equals 0 into this equation, you can see that the interaction picture, the state vector in the interaction picture at time 0 is the same as it is in the Schrodinger picture. The initial conditions are the same in both pictures. In any case, let's define W then as a time evolution operator in the interaction picture. We can express W, as it turns out, in terms of U and U0, the U and U0 solution of these equations. That's easy enough to do, because psi in the interaction picture, by the definition, if I just write it out, is U0 of T dagger applied to psi in the Schrodinger picture. I'm just really copying the equation above. But psi in the Schrodinger picture at time t is equal to U of T times psi in the Schrodinger picture at time 0. And as I just explained, that's the same thing as psi in the interaction picture at time 0. So multiplying this out, you see that U0 dagger times U is the same thing as W. Let me write that down here as a W of T is equal to U0 of T dagger times U of T. And I'll box that because that's the relationship between these various time evolution operators that we're seeing here. So to evolve in the interaction picture, one can say that what you do is you evolve forward by the exact evolution for a certain amount of time, and then you evolve backwards by the unperturbed evolution by the same amount of time. Okay, so this is how that works. Now let's see here. If we yeah, okay, so here's what I think I want to do now is I'd like to show you to say some things about the S matrix, because the interaction picture gives you an interesting perspective on the type of problems that the S matrix addresses. Let's think about a scattering problem. We've got some potential over here. Let me call it V of R. It doesn't have to be rotationally invariant. It can be lumpy. We send in a wave packet. We launch a wave packet at it, traveling in like this at some distance at some launch time like this. Now, in scattering theory, we normally assume that the potential dies off with distance at some rate. Has to die off fast enough. And so, as a practical matter, in practical situations, this means that when we launch the wave packet at the potential, we're normally at a sufficient distance that the wave packet does not overlap with the potential at all, or negligibly anyway. So what that means is that initially the wave packet evolves according to the free particle Hamiltonian. You might as well just say it also evolves according to the exact Hamiltonian. It doesn't make any difference because potential has no effect if it doesn't overlap with the potential. So either one is okay. But let's say it evolves according to the unperturbed Hamiltonian. So let's understand, let's try to develop a mental picture of this scattering situation, working first in the Schrodinger picture. I think I gave the same picture, the same description in my last lecture, so I'm repeating myself, but let me do it anyway. So this wave packet then evolves initially by the unperturbed Hamiltonian. We know what that means. It means that there's an average velocity, it moves forwards. We also know the wave packet spreads, or as a matter of fact, it might shrink. That's a possibility too. But if it does shrink, it reaches after a while some minimum point, and then it starts to expand again. Usually it's expanding as in wave packet evolution, free particle evolution. We had a homework problem on that last semester, so I assume you know all about that. All right. Now what happens after a while, of course, is the wave packet begins to overlap with the scatterer. And when it does that, it's going to start to generate a scattered wave, which is going to radiate out in various directions. Some of them are forward directions, some are backwards, and so on. You can picture it looking something like that. The details of what happens are going to depend on how large the wave packet is compared to the scatterer itself. If the wave packet is much larger than the scatterer, then you can imagine that there are, on the wings of the wave packet, it just kind of goes straight through without being affected very much by the potential. But the parts of the wave packet that are on target are going to get strongly scattered, and you'll have a scattered wave go out. Now, as we wait a longer and longer time, what happens is that the wave packet eventually comes in and more or less it either all passes by or else it gets scattered out. And then there's no more wave packet coming in because it's all used up. And if you continue to wait, what happens is the scattered wave radiates away from the scatterer and the forward wave just keeps on going, what's left of the wave packet. And so after a while, the wave function, it's no longer a wave packet in the usual description of things because it's not localized anymore. But nevertheless, what happens is the wave function moves away from the region in which the potential is active. And so at late times, what happens is that the time evolution is once again governed by the free particle Hamiltonian, because the wave function no longer overlaps with the potential. Now, let's say, to be specific, that it happens at some time around t equals 0. Let's set the clock so that when the wave packet is strongly interacting with the potential, let's call that t equals 0. So what that means then is at large negative times, we launch the wave packet at large negative times, the evolution is governed by the free particle evolution. And likewise, at large positive times, it's also governed by the free particle evolution. If you let let's say the positive time go to infinity, what happens to the wave packet or wave function? Well, the scattered wave radiates out. It's only a pulse of a scattered wave. It just moves further and further away from the scatterer. It'll just keep on moving on to further remote regions. The wave packet will spread out. The density in any particular place in space will go to 0. This is the same thing true for the wave packet going downstream. It spreads out too, what's left of it going downstream. So in the distant future, the wave function actually does not approach a definite limit. It just thins out ever more and removes itself spatially ever greater and ever distances from the scatterer. So there really is no large time limit as t goes to plus infinity, nor as you go to t goes to minus infinity is there such a limit either, for the same reason. All right. Now, on the other hand, as I've mentioned in the interaction picture, the evolution due to the unperturbed Hamiltonian is stripped off. So at early times, at large negative times, when the wave packet is evolving according to the free particle evolution, if we look at that in the interaction picture, the wave packet doesn't evolve at all. So look at the scattering problem in the interaction picture. The initial state is just a state vector, a wave function that doesn't change at all. Not until in the Schrodinger picture, the wave function starts to overlap with the potential. Then you start to get an evolution in the interaction picture, because now there's a difference between the u of t and the u0 of t, insofar as its action on the wave function is concerned. So the wave function does evolve in the interaction picture. However, once the wave function starts to leaves the region where the potential is active, then once again, it's governed by the free particle in the Schrodinger picture, governed by the free particle Hamiltonian, which means that in the interaction picture, once again, it does not evolve. So what this means is that if I have the interaction state psi I of, let's call it capital T here. No, let's do it this way. Let's write psi I of minus capital T as we let t goes to infinity. So we move further and further back in time. There is some negative time before which the wave packet evolution is governed by the free particle. And what that means is that in the interaction picture, the wave function is constant for those times. So what that means is this limit exists. There's a definite state there as t goes to minus infinity. And for the same reason, there's another limit for ti given by ti plus t as t goes to positive infinity. There's an asymptotic state there, and the limit does exist. These are limits that don't exist in the Schrodinger picture. They exist in the interaction picture. And so there is a linear transformation between the asymptotic state at psi sub I in the interaction picture at large negative times, and that at large positive times. Let's work out what that is. So psi I of t, that's capital T, what does that equal to? That's given by W of t acting on psi I of 0, where W of t is the time evolution operator in the interaction picture. And likewise, psi I of minus capital T is equal to W of minus t on psi I of 0, like so. And so I can solve for psi I of 0. Let's say, which way do I want to do it? I want to solve for it here in the second equation. I have psi I of 0 then is equal to W of minus t dagger, which inverse is dagger because they're unitary operators, times psi I of minus t. And then plugging that into the upper equation here, what we get is that psi I of t is equal to W of t times W of minus t dagger times psi I of minus t, like so.
Professor?
Yes.
Did you say that psi I of t and psi I of minus t are both like t is going to positive infinity for both of them?
Well, the formulas I'm writing down are valid for any value of capital T, but we're interested in the case in which capital T goes to infinity. So one of these represents the asymptotic state at large negative times, and the other one is the asymptotic state at large positive times. So what we're interested in is a linear transformation that maps you from one to the other.
Okay, thank you.
This is a description of the scattering process you see in terms of wave packets, which are normalizable states and therefore physical states.
Gotcha. Thanks.
So this product of operators here is usually called the S matrix. The S matrix is really an operator, but they call it a matrix because people usually talk about its matrix elements. Anyway, let's just call it S. And so let me let's work out an expression for S. So the W of T, I'll remind you, is given by U0 of T dagger, this capital T now, times U of T without a dagger. So this is equal to U0 of capital T dagger times U of T. That takes care of the W of T part. And then W of minus T dagger is going to, so W of minus, put in minus T here. W of minus T is equal to U0 of minus T dagger times U of minus T. And so then daggering that, I need to reverse the order. So I get U of minus T dagger times U0 of minus T now without the dagger. Okay, that's what the S is equal to. S is equal to this is the limit as capital T goes to infinity. Now, the daggering of U is the same thing as replacing U by U inverse. That's assuming this potential is time independent, so that both the unperturbed and the exact evolution are obey the composition rule. And so this U of minus T dagger is the same thing as U of T. And this U0 of minus T is the same thing as U0 of T dagger. And if I put this together, then what I get is the expression that S is equal to the limit as capital T goes to infinity of U0 of T dagger times U of double T, twice T, times U0 of T dagger, like so. And this is one of the ways of defining the S matrix in scattering theory. And in any case, the main point that I want to make right now is that this is gives you an interesting point of view in the interaction picture, is that it allows you to understand why these limits, sometimes these are called in states and out states, why these limits in the interaction picture actually exist. It's because U of T and U0 of T do the same thing if the wave packet or the wave function does not overlap with the scatterer. So that applies for both large positive and negative times. So applying one and then the inverse of the other just cancels out and gives you nothing. In any case, this limit then exists, or at least the limit exists when the limit of the wave, if this is applied to a wave packet, then the limit of this operator acting in the wave packet as T goes to infinity, that limit exists. You can see what this involves is it involves, first of all, taking your wave packet, moving it backwards by the free particle Hamiltonian by a large time. That means like a large negative time, then moving it forward by twice that time. That's enough to take it forward into the scattering region and then out beyond again, so it's free once again, and then moving it backwards again under the free particle evolution from that forward time. In any case, that's the meaning of the S matrix. Now, this is really just a diversion or a digression from the subject of time-dependent perturbation theory, which I want to talk about tonight. But I wanted to bring it in because it's an interesting perspective on the interaction picture. So let's talk about time-dependent perturbation theory. The idea is that in the interaction picture, psi I of T, which is equal to this W of T times psi I of 0, evolves more slowly than the corresponding state vector in the Schrodinger picture. And this gives us an avenue for carrying out perturbation expansions on the time evolution. In particular, let's work out what the time evolution is. To do that, we'll work out a version of the Schrodinger equation here. To do that, I'm going to write this in the following way as U0 dagger of T times psi Schrodinger of T. This was the original definition of psi in the interaction picture, and it's equivalent to the line above. If I now apply IH bar ddt to both sides, because I want to get some version of a Schrodinger equation, that operator applied to psi interaction of t on the left-hand side, we can just use the chain rule on the right-hand side. You get IH bar ddt of U0 dagger multiplied times psi Schrodinger of t plus U0 dagger of t times IH bar ddt applied to the Schrodinger state vector. Writing it all out like so. Now, as far as this first term is concerned, we need the derivative of U0 dagger. A minute ago, I gave you the derivative of U0. Here it is. If I dagger this equation, let me put it down here where I have some space. You can see you get minus IH bar du0 dagger dt, dagger both sides, is U0 dagger times H0. So I can bring the minus sign over the other side. So if I do that, this thing here becomes, with a minus sign, it becomes minus U0 dagger times H0. Whereas this equation, this derivative on the right hand side is just use the Schrodinger equation in the Schrodinger picture, and this is therefore the Hamiltonian H acting on psi Schrodinger of t, which I'll write this way as H0 plus H1 times psi Schrodinger of t. All right. Now, or let me write it this way as H0 plus H1. Let's see. Yeah, this is fine. I'll just leave it that way. H0 plus H1 times psi Schrodinger. Now, if we look at this term here, the first term, it's minus U0 dagger H0 times psi Schrodinger. Whereas on the right-hand side, I've got plus U0 dagger H0 times psi Schrodinger. And so this term here, which is the same as that term, cancels out with the H0 part of the second term. And so putting this together again and cleaning this up, we have IH bar ddt of psi in the interaction picture is equal to now just the H1 part of the second term. So there's, first of all, a U0 dagger of t, and then there's an H1, and then there's a psi Schrodinger. Now in here, I'm going to insert a U0 of t times a U0 dagger of t. Because if I do that, then let me write it out here, IH bar ddt of psi in the interaction picture. Look at what we've got. We've got U0 dagger U0 sandwiched around H1. That's H1. This H1 is understood to be in the Schrodinger picture. I didn't write the S subscript on it. But when I conjugate it with the U0, it converts it into the interaction picture and gives it a time dependence. It becomes H1 of t, H1 interaction of t. Then what's left is U0 dagger times psi Schrodinger, which is psi interaction. And so this is a derivation then of a version of the Schrodinger equation in the interaction picture. And it's quite a simple result. It says that in the interaction picture, the state vector evolves according to the just the H1, just the perturbing Hamiltonian. H0 is gone, but the perturbing Hamiltonian is represented in the also in the interaction picture. So if you think of H1 as being small or operating over a limited period of time, that's true in both pictures. So what you see as you gain what we wanted is that now the psi interaction is evolving more slowly than it did in the full picture, in the original Schrodinger picture. All right, so this is the basic Schrodinger equation in the interaction picture. Now, because H1 in some sense is going to be small or of limited extent in time or space, this suggests that we might be able to develop a perturbation expansion in powers of H1. And indeed, we're going to do that. That's exactly what we're going to do. It doesn't mean these perturbation expansions converge or even that they necessarily work very well in all circumstances. It depends on what H1 is, and sometimes they don't. But there are cases where it does. And this is simple to analyze, so we're going to take that case first. This leads to a perturbation series, which is called the Dyson series, named of course, after Freeman Dyson, who died recently. In any case, the way to handle this is to imagine taking this differential, the Schrodinger equation, and integrating it from 0 to t dt prime, integrating over time between two limits 0 and t. In fact, allow me to rewrite this equation, just simply replacing the t's by t primes, which will be convenient to do, is h1 odd. It's just a dummy variable. Let me do it that way. psi interaction of t prime. Because now I can integrate with respect to t prime, integrate both sides. And if I do, oh, and by the way, let me do something else too. Let me take the IH bar over to the other side, whereupon it becomes a 1 over IH bar as a prefactor. Allow me to do that. I hope this is, I hope I'm not scrunching up too much because I kind of didn't leave myself enough space here. But now if I integrate the left-hand side, let's put a colon here, meaning I'll apply this integral to both sides. Applying it to the left-hand side, we get psi interaction at time t minus psi interaction at time 0. And on the right-hand side, we get 1 over IH bar integral 0 to t dt prime, H1 interaction at time t prime times psi interaction at time t prime. Okay. Now let's have an abbreviation for the psi interaction at time 0. Let's just call it I here, lowercase I, which just means initial state. I'll say more about that initial state in a minute, but let's just make that simple change. If we do, then we can write what we just derived by writing psi I of t is equal to the initial state plus the integral from 0. Here, let me do it right. Let me get it on a clean piece of paper. We get psi I of t is equal to the initial state I plus 1 over IH bar, the integral from 0 to t dt prime of H1 interaction of t prime multiplying psi I of t prime. Okay. So this is an integral equation, which is exactly equivalent to the Schrodinger equation in the interaction picture. But you can see that it's got the initial conditions built into it. Just to differentiate, it reproduces the Schrodinger equation, and to integrate, on the other hand, reproduces this. So the two equations are completely equivalent. It's got a psi I of t on the left-hand side, but it's not a solution for that because the psi I of t also appears on the right-hand side. However, if we think of H1 as being small, then the second term is a correction term. It's a correction term to where you started off with the initial condition. Obviously, if Hn or H1 were equal to 0, then psi I would be equal to I forever, initial state I forever. So this gives you the correction to that due to non-zero H1. We can get another, so in a sense, this could also be regarded as an approximation. If I just completely neglect the first term, this gives us our answer, correct order 0, which is the initial state. We can obtain another equation which can be used to improve the approximation by taking the left-hand side and substituting into the right-hand side. In order to do that, I need to take the variables t and replace it by t prime, which I need then to replace by t double prime, changing variables so that I have a formula for psi I of t prime that I can plug in there. If I do, what I get is another equation, which is still exact. This is that psi I of t is equal to the initial state I plus 1 over IH bar integral 0 to t dt prime H1 interaction of t prime times the initial state I plus 1 over IH bar squared, a second order integral 0 to t dt prime integral 0 to t prime dt double prime H1 interaction of t prime times H1 interaction of t double prime multiplying onto psi I of t double prime. And this equation is also exact. But now you see the unknown wave function psi I has been pushed to a second order term. If I now take the original equation and substitute the psi I of t with juggling of primes on the time variables, substitute it into the right hand side here, I can push the unknown wave function to third order and so on. Ultimately, what this does is it generates a series, which is called the Dyson series. If I carry it out to third order, this psi I of t double prime here would get replaced by the initial state I, and then we'd have 1 over IH bar cubed here, and then we'd have 3 integrals, which I won't write out explicitly, and 3 products of h's, and so on, plus dot, dot, dot. And this series, which is created in this way, is called the Dyson series. In the notes, I developed the Dyson series for the time evolution operator, and here I'm doing something a little simpler, which just to develop it for the state vector psi of t. All right. So this is obviously some kind of a power series expansion of the solution in powers of H1. Here's a linear term, quadratic term, the next one is cubic, and so on, expressed in terms of these integrals. And this will be the basic perturbation series that we'll be using for time-dependent perturbation theory. All right, now, any questions about that so far?
I have a random question.
Sure.
Is this the same Dyson as like Dyson spheres?
Same Dyson as in what?
Like the Dyson spheres, like the
Oh, the Dyson
energy
sphere.
from the
Oh yeah,
star.
sure. Like how to live in outer space.
Yeah.
Yeah, I'm sure it is the same Dyson. I think there's only one. He was an interesting person. You know, he never got his PhD. He's probably the only outstanding physicist ever in since the 20th century anyway, for whom that was true. Anyway, he didn't. Many people felt he should have got a Nobel Prize for his work in quantum electrodynamics. Schwinger, Feynman, and Tominaga did so, but not him. He was a curmudgeon. He was something of a climate skeptic. I never quite figured out exactly what that meant. I mean, because he didn't deny that CO2 was warming the Earth's climate. I think he just felt it wasn't so bad, or maybe he just didn't like the people that were worried about it. I'm not sure. Anyway, he was he had a personality. Let's just put it that way. Okay, so anyway, that's the Dyson series, or it's a version of it anyway. Now, in what I'm going to call the usual problem, the initial state I is actually an eigenstate of the unperturbed system. So let me talk about the unperturbed system H naught. Let's say it's got eigenstates n with energy E sub n. We'll assume it has a discrete spectrum for simplicity. And this is kind of a general notation for the eigenstates and eigenvalues. As a special case, we'll take the case where n is equal to I. This is the initial state. So H0 acting on the initial state brings out the initial energy E sub I times the initial state. It's just one of the many states, all right? And we'll henceforth assume that this I state here is this eigenstate of H0. Let's also take the state vector in the interaction picture, and let's expand it as a linear combination of energy eigenstates with coefficients I'll call Cn, which have to be functions of time, like so, Cn like this. Let's make this expansion. If we do this, we can solve for the expansion coefficients by multiplying through by the n vector as a bra. And what we get is that Cn of t is equal to n scalar product with psi I of t. All right. But on the other hand, the psi I of t is equal to n times the time evolution operator in the interaction picture, what we call W of t, acting on the initial state I, like so. And so what we can see is that these Cn of t's, these expansion coefficients in the interaction picture, are actually transition amplitudes, but measured in the interaction picture. That is to say, the time evolution operator in there is the interaction evolution and not the Schrodinger evolution operator. But these are transition amplitudes. We can convert this to the Schrodinger picture, however, because W is equal to U0 of t dagger times U of t. And if you let this U0 act to the left on an eigenstate of H0, it'll bring out a phase factor, which is e to the I E sub n t over H bar. And so what we obtain then is an expression for the transition amplitude in the interaction picture. It's equal to E to the minus plus I E n t over H bar times the matrix element between initial state n and I of the time evolution operator in the Schrodinger picture. This is what I originally spoke of at the beginning of this lecture as the transition amplitude. So the only difference in the transition amplitudes between the interaction picture and the Schrodinger picture is this time-dependent phase factor. And that means in particular the transition probability, which is the square of the amplitude, is the same in both pictures. So the transition probability, which I'll denote by a p then, p at p sub n of t, is equal to the absolute value of Cn of t squared. And it's the square of the transition amplitude in the interaction picture. All right, now then, So to bring my last page back, this is the definition here of the transition amplitude. What we now see is the transition amplitude in the interaction picture. It's also the expansion coefficients here. It can be obtained by sandwiching or forming the scalar product of state n with psi I of t. However, psi I of t is given by the Dyson expansion. And so I want to contemplate now taking the Dyson expansion and multiplying through on the left by the bra in, like so. Let me put a colon here to indicate we're going to multiply through. So on the left-hand side, we'll get the transition amplitude. And the first term on the right-hand side is going to be a Kronecker delta, and then we'll have first, second, third order corrections and so on. So allow me to write this out in the following way, which is that Cn of t is equal to a Kronecker delta Ni plus Cn at first order of t plus Cn at second order of t plus ... where the numbers in parentheses indicate the order of perturbation theory. And if I do this, then I get explicit expressions for the corrections to the transition amplitude at various orders. So for example, Cn1 of t is 1 over I h bar, the integral from 0 to t dt prime of the scalar product of n on the left, h1 interaction of t prime in the middle, and the initial state I on the right. At second order, Cn2 of t is 1 over I h bar squared, quantity squared, the integral from 0 to t dt prime, the integral from 0 to t prime dt double prime. And then we have the scalar product n on the left. We've got h1 interaction of t prime, h1 interaction of t double prime, two powers of h1, and then the initial state I, and then et cetera. You can see the pattern here. So these then are explicit expressions for the first, second, and so on order corrections to the transition amplitude. All right. Now then.
So I'm wondering, like, so when we did time independent perturbation theory,
Yes.
And then we had our series expansion in terms of lambda, then you're like, I think you said that lambda is kind of like h bar because, and what we're doing is like an expansion in h bar. And since h bar is small, it's fine. But here h bar is in the denominator.
No, I don't think, I don't know if I ever said that. I didn't mean to. H bar is the expansion parameter in WKB theory, but in bound state perturbation theory, the parameter is, I called it lambda. It's a formal interpolation parameter that takes you between H0 and H0 plus H1. So that's not the same as H bar.
Okay,
I mean, normally in bound state perturbation theory, one is not expanding an H bar.
All right, I might be confusing the two then. Yeah.
Okay. So I didn't put in any lambda here, but you can see that this is the Dyson series is in effect an expansion in powers of H1. It's clear from the formulas. All right. Now,
Dr. Littlejohn?
Yes.
How can you guarantee that the P's are probabilities if you're only up to like first order because of normalization reasons?
Yeah, so you have to worry about if I truncate the P expansion, I mean, if the expansion would converge, then the P is going to be the probability, and it'll square and add to 1. But if we truncate the series, then when you square it, you're just going to get an approximation to the probabilities, and there's no guarantee it'll add up to 1. Is that what you're saying?
Yeah, I think so. Thank you.
Yeah, well, that's certainly true. Actually, as we'll see, there's a further problem too, which is that not only are these approximations, but the approximation actually goes bad if you wait long enough. There's an upper time limit on how long the approximation is good. Actually, that depends on the problem, but for some problems that's true. And beyond this upper time, you get errors basically. You can get, for example, you can get violations of unitarity and get probabilities that are nominally greater than 1. All right. But in any case, for short times, these expressions are valid. All right. Now, the interaction picture is convenient for carrying out this expansion, but for actual calculations, the Schrodinger picture is more convenient. If I take a look, for example, at the first order term in this matrix element here, let's take this down and let's transform it into the Schrodinger picture. this is the same thing as in the writing H1 interaction in terms of the Schrodinger picture. I have a U0 of T dagger. It's actually T prime. And then I've got H1 in the Schrodinger picture, and then I've got U0 of T prime on the other side. And then I've got I like this. H1 in the Schrodinger picture might also depend on time. I could put that in if you want. Some problems it does and some problems it doesn't. Most of the problems I'm going to be considering in this lecture tonight and also in the next lecture will be ones in which H1 does not depend on time. But to give you an example of a problem where H1 does depend on time, you can think of an atom in a light wave. It's a very common problem when you're dealing with lasers interacting with matter. An atom in a light wave. In that case, the H1 are the terms in the Hamiltonian that involve the interaction with the external electromagnetic field, which is the light wave and is therefore time dependent. So these are real problems and are very important in practice. But initially, at least, I'm going to deal with problems in which H1 is independent of time. Anyway, to make a long story short, it either may or may not, depend on circumstances, depend on time, H1 in the Schrodinger picture. But in any case, here's splitting off the U0 to the right and the left. Now the U0 dagger can act to the left on an eigenstate of H0 and bring out a phase factor. The U0 on the right can act on another eigenstate of H0 and bring out a different phase factor. And if you do this, the answer can be written this way as e to the I times the frequency, which I'll write as omega ni T prime, times the matrix element of the H1, which is now in the Schrodinger picture, which I'll allow to be a function of time, like so. Where the omega ni is equal to En minus EI divided by H bar, something I'll call the Einstein frequency to give it a name. This is maybe crediting Einstein with more than he deserves in this case, because certainly Planck was thinking about E equals H bar omega, but Einstein attached that to the notion of photons as particles. And these, of course, is the frequency of the photons that are emitted in transition. So this is the idea we're thinking about here. All right, in any case, to give it a name, we'll call it the Einstein frequency. And so this then appears. And so we can do this with this expression here. And if we do, then at first order perturbation theory, Cn1 of t is equal to 1 over IH bar, the integral from 0 to t dt prime of e to the I omega ni t prime times the matrix element now in the Schrodinger picture, like so. This is the C1 in the Schrodinger picture. That's for C1. For C2, it turns out to be convenient to do an insertion of a resolution of the identity of the unperturbed system between the two factors of H, which are at different values of time. And then we convert each of those from the interaction picture into the Schrodinger picture, which brings out phase factors. And if we do, then we get an expression for Cn2 of t, which is this. It's a 1 over IH bar squared. It's a double integral 0 to t dt prime, integral from 0 to t prime of dt double prime. Then we have a sum over states k. Then we have a phase factor e to the I omega n k t prime, plus another phase e to the I omega k I t double prime. You see this connects, these states k, by the way, are called intermediate states. So the first phase factor connects the final state n with the intermediate state k, and the second phase factor connects intermediate state k with the initial state I. And then this is then multiplied by the product of matrix elements in the Schrodinger picture, NH1K, KH1I, like so. All right. Now, later in the course, we're going to have opportunities to deal with second order time-dependent perturbation theory, but that's several weeks down the line. And so for now, I'm going to just post this result as something we'll come back to for the C2 result anyway. And we'll focus just on the first order perturbation theory and solve some problems which can be solved at first order. So let's do that. That'll occupy us for tonight. So let's just take care of the C1 expression. Now, without knowing the dependence of H1 on time t prime, you can't do much with this integral. But what I'm going to do moving forward is to assume that H1, which is now in the Schrodinger picture, is time independent, in which case the matrix element just can be taken out of the integral. And what's left over is an elementary integral. It's just an integral of an exponential. And if you do it, what you end up with is this, is you end up with Cn of t is equal to 2 over IH bar, e to the I omega ni times t over 2 times the sine of omega ni times t over 2 divided by omega ni. And then there appears the matrix element, which was independent of time, and so came out of the integral. So for Hamiltonians which are independent of time in the Schrodinger picture, this then is the transition amplitude in the interaction picture at first order. There's a zeroth order term, which is the Kronecker delta, remember, between initial and final states. This is the first order correction. All right. In fact, the Pn of t is the square of this. This is Cn at first order here. This is the square of the Cn, so that's delta Ni plus Cn at first order of t plus Cn at second order of t, and so on, plus dot, dot, dot squared. And if we have n not equals to I, which means that the end state is not equal to the initial state, then the delta Ni goes away. And if we work also at first order only, then you see what you get is you get Pn of t is just equal to the square of Cn1 of t. And I can then square this expression. And what I get is 4 over h bar squared from the 2 over I h bar squared. The phase factor with omega ni goes away. We have sine squared omega ni t over 2 divided by omega ni squared. And then we have the square of the matrix element, which is now in the Schrodinger picture. And let me box that because this is the transition probability under the conditions given here. All right, and this is the expression that we'll use for actually solving some problems tonight. If we have time, we will anyway. Let me bring this over, you can see the whole thing. All right, so this is the transition probability. You can see the transition probability to state n as a function of time involves a certain time-dependent factor here, which depends on the initial and final states n and I, but only through the energy, because to write it out again, the omega ni is the Einstein frequency, just depends on the differences in the energies, the n minus the I over h bar. And as far as h1 is concerned, it appears in the square of the matrix element. So all the details about h1 appear over there. Also, as far as the dependence on the initial and final states is concerned, the time-dependent factor that sits out front, it depends on the initial and final states only through their energies. Whereas the matrix element over here will depend on other properties of the initial and final states in general, such as not just the energy, but the momentum, the direction of the momentum, the spin, the polarization, things like that, other details of those states. The first thing to look at is this time-dependent factor that appears there, so we can understand that. What is that telling us? To do that, I want to make a sketch of this function. I can suppress the ni subscripts on this, and let's see if I have enough room to make a sketch of this function here. See how good my artistic skills. I can tell you my artistic skills are not very good. Let's plot the function sine squared. Block this off here. Let's plot the function sine squared omega t over 2 divided by omega squared. And let's get a horizontal axis down here, which is the omega, and plot it as a function of omega. Now the omega being the Einstein frequency has now disappeared. Oh yes, it's right here. The omega being the Einstein frequency connecting the initial and final states is proportional to the energy difference between the initial and final states. These are the initial and final states of the unperturbed Hamiltonian. But in many circumstances, the system overall conserves energy, so that the energy of the final state, one would expect the energy of the final state should be equal to the energy of the initial state. And so there's a question about why we ever consider En not equal to Ei at all. I'll try to clarify why we need to do that. Part of the answer to that is that in this analysis that we're going to carry out, our goal is to solve the Schrodinger equation. We let the solution of the Schrodinger equation tell us everything we need to know. We don't try to force energy conservation on it. However, part of the answer also, part of the discussion also concerns the fact that in quantum mechanics, the energy of a system is only defined if you don't look at it or you let it evolve on its own for an infinite amount of time. If you only let it evolve for a finite amount of time, then the energy is uncertain by an amount which is delta T over H bar. All right, so those are issues that need to be considered here. In any case, keep that in mind, that this Einstein frequency is a measure of in effect how much energy is not conserved on going from the initial state I to the final state N. So that's the meaning of the omega axis here. This function has a sine function which oscillates between plus and minus 1 and a 1 over omega squared, which you can think of as an envelope. Let me do my best to kind of sketch an envelope here. It comes down like so. And then on the other side, it'd be good if I could make it symmetrical, but I probably can't because my hand is too old and feeble and crotchety now. In any case, we have an envelope for 1 over omega squared that looks something like this. The function goes to 0 at times, which are given by t is equal to 2n pi over, excuse me, function as a function of omega, which is how we're plotting it, goes to 0 to omega values, which are equal to 2n pi divided by t. So I've got a 2 pi over t here. I've got a 4 pi over t here. I've got a 6 pi over t here. I've got similar things on the negative side, minus 2 pi over t and minus 4 pi over t and so on, minus 6 pi over t. The function is 0 at those nodes. If I take the limit at which omega goes to 0, then the sine function, you use a small argument value of that, and you get omega squared t squared over 4 divided by omega squared, you just get t squared over 4. So the maximum value of this function here at t, that is to say at omega equals 0, is t squared over 4. Depends on the time. So the function looks something like this. It has a maximum here. Let me try to draw on the left side first. There's a maximum here, it comes down, it sort of becomes tangent to this curve halfway through. Comes down like that, goes through 0 there, rises up here, then goes down through 0 there, rises up again, goes down to 0. On the other side, it's symmetrical, so it does something like this. In spite of my bad drawing, this is the idea. This is what the function looks like. Okay. So if we consider energy conservation, as to say En equals Ei as being, let's quote unquote, on resonance, then moving away from out to positive omega means moving further and further away from resonance. If we're far away from resonance, then the envelope 1 over omega squared is small. And what we see is the transition probability then oscillates at a relatively high frequency, because omega is large, relatively high frequency. So out here, the transition probability just moves up and down rapidly, like so. But if you decrease omega, move closer to resonance, then the amplitude of the oscillations increases and the frequency decreases. So now you're oscillating more slowly here. As you come closer to resonance, the amplitude starts getting really big, but it also starts to do really slow oscillations with large amplitude. And exactly on resonance, the amplitude in effect goes to infinity and the frequency goes to 0. That's why we end up with something that doesn't depend on omega at all there. That's the idea. So that gives you the idea of the transition probability as a function of time, depending on the energy of the final state, how far away you are from the initial energy. All right. That's for a fixed value of, that's looking at the time dependence for different values of omega. Now then.
Excuse me, can I ask a quick question?
Yes.
I'm a bit confused on how this fits into what we learned about bound state perturbation theory before. We're still considering the case where E1 is time independent, right? And all these Cn coefficients are in the Schrodinger picture, right?
The Cn coefficients are in the interaction picture.
Oh, okay.
But at this stage, we're not actually trying to find an eigenstate of H0 plus H1. In fact, as we'll see, time-dependent perturbation theory is most often useful in dealing with problems in the continuum where we don't have bound states. So in the continuum, it doesn't make any sense to say what happened to the shift in the eigenvalue, because you just have a whole continuum of eigenvalues. And this in fact is the class of problems we're going to be dealing with mostly. In fact, most of the problems we'll deal with for the rest of the semester are like that. Okay.
Okay, I see.
All right.
Thank you.
But you'll see that we'll be playing a game here and going through bound states in order to get to continuum states. All right, now as we let t get larger, what happens is that the envelope stays, the envelope's 1 over omega squared and stays the same. But these nodes of the wave function move in like so. They move in closer and closer and get tighter and tighter. So these oscillations get shorter and shorter wavelength. In particular, notice what happens to the central lobe. The peak of the central lobe goes upwards in proportion to t squared. And what about the width of the central lobe? Well, it's the distance between plus and minus 2 pi over t. So it's basically 2 pi over t at the halfway up, if I look at the halfway mark. So the area of the central lobe, is equal to the, or roughly anyway, is an order of magnitude. It's given by the width, which is 2 pi over t, times the height, which is t squared over 4. And therefore, that multiplies out to be pi over 2 times t. Therefore, the area of the central lobe grows in time. And that means that there are more and more transitions to states that are closer and closer to being on resonance as time goes to infinity. The majority of the states end up getting, the largest fraction of the states end up getting closer. If you like ask for 99% of the states, where do they go? They end up getting closer and closer to being on resonance the longer you wait. Okay. Now, so it's like this function is approaching something like a delta function multiplied times time. That's the idea. And it approaches that limit, and the limit that t goes to infinity. To formalize this, allow me to do the following thing. Let's write sine squared omega t over 2 over omega squared, which is the function we're interested in. Let's write this as pi over 2 times t, and then the function that's left over, let's call it delta t of omega. The argument I've just given indicates that the limit as t goes to infinity of delta sub t of omega is actually a Dirac delta function in omega. We factored out the t here, which takes care of the fact the area grows in proportion to time. Taking that out, what's left over is the area which is independent of time, but becomes sharper and thinner as t goes to infinity, and so the limit is a delta function. Now, to show that this is actually the right answer, what we need to do is to integrate this function from minus infinity to plus infinity, d omega of sine squared omega t over 2. I mean, this statement which I just made here, I didn't derive at all. I just argued that as an order of magnitude, the area was, pi over 2 times t. But to be more precise about that, if we do an actual integral of our function, the function we're interested in over frequency, over all frequencies, you can do this integral by contour integration. And indeed, it turns out to be exactly pi over 2t. So that justifies this limit here, where delta of t is defined by that formula. So this will be a convenient way of handling this function when t is not infinite. We're going to ultimately be interested in taking the t goes to infinity limit, so we get delta functions. As you can see, omega equals 0 is the resonance condition. So this delta function is in effect an energy conserving delta function, and will bring about energy conservation on our dynamics. All right.
So that's essentially saying there is no transitions at t equals infinity, because it's all just from the initial state to the initial state at that point?
No, because in the continuum, there will be many states of the same final energy. But see, there's a continuum of states. So if you just make t very large, but not infinite, then there's a little energy range around, a little energy thickness, but it's not 1D. It's like the states are typically in multidimensional space. So there's like a shell of states. For example, in scattering theory, you have outgoing states that can go out in different directions. In the limit that t goes to infinity, those outgoing states have the same energy as the incident state. That's conservation of energy in the scattering process.
Okay, I see. Thank you.
All right. Okay. So anyway, these are the properties of this function. All right. Now, in the next phase of this presentation tonight, I'd like to do an application to scattering theory. So let's set the problem up. Let's see. Yes, here's how we'll do it. let's say we've got a potential, we'll make this potential scattering in 3 dimensions. Here's coordinates X, Y, and Z. I'll call the potential U of R, not V, because I'll reserve the symbol V for something else. We'll call this U of R. We'll assume that U of R goes to 0 as R goes to infinity fast enough to make the arguments that we need to make true. I won't be quantitative about that, not at this point. But in any case, U of R dies off sufficiently rapidly as the radius goes to infinity. It may be a lumpy potential. We're going to send in, launch against this scatter, we're going to launch a plane wave with initial wave vector ki like so. K, the I stands for incident, and it will hit the scatter and give us a scattered wave. That's the problem we want to analyze. We're going to use a Hamiltonian. H is equal to p squared over 2m for the free particle part, and then the U of R for the scatterer. And this will be the H0 and the H1 for our problem. Now this gives us a problem right away because this H0 is a free particle Hamiltonian, which doesn't have a discrete spectrum. It has a continuous spectrum. And yet the analysis of time-dependent perturbation theory, which I've just presented to you, was based on the assumption that H0 had a discrete spectrum. In some problems, H0 does have a discrete spectrum. Again, to go back to the atom and the light wave, if you're talking about the bound states of the atom, you may very well be interested in what the light wave does to them. It's a very common problem in practice. So in that case, the H0 really does have bound states. But for this problem, the H0 we're really interested in doesn't, it's got a continuum. So we're going to fix this by using the mathematical crutch. Shouldn't blame it on mathematics, the crutch of going to box normalization. The idea is that we divide the universe into cubical boxes, all of which they're all large and of the same size. We'll call L as the width of the box, like so. So the volume of the box is equal to L cubed. We're going to be interested in the limit where the volume goes to infinity, ultimately to get physical results. And we're going to assume that all the physics, including the potential and the wave functions, are periodic in the boxes. And we'll solve that problem. This gives us a discrete spectrum for H naught. Then we take the limit that V goes to infinity to get physical results. That's the plan. All right. So the wave functions in the box satisfying periodic boundary conditions, if I write them as psi sub k of x, no, let's write it this way. Psi sub k of r, I'm using r tonight for the position variable. This is a plane wave, e to the I k dot r. And the wave vector k, in order to be periodic inside the box, must be equal to 2 pi over L times an integer vector n, where the integer vector n consists of components nx, ny, and nz, each of which is an integer that ranges between minus infinity and plus infinity to give you different choices for k. So there's a discrete set of k values, and this gives us a discrete spectrum of the Hamiltonian H0 with periodic boundary conditions. If we do this, we need to divide this wave function by the square root of the volume of the box if we want to normalize it over the volume in the box. That means that the scalar product of k with k prime is equal to 1 over volume v, the integral over the volume v, d cubed r of e to the minus I k dot r times e to the I k prime dot r. And this is a Kronecker delta in k and k prime. Kronecker delta, not a Dirac delta function because k is discrete. You see, it takes on these discrete values. So this is the normalization that we'll use. So this basically makes the states orthonormal under a normalization within the box. All right. Now then, we have our initial state ki with our initial plane wave coming in. The scatterer is down here in some small region inside the box. Since we're going to let the box get very big, we're going to let the size of the box go to infinity. We can imagine that the size of the box is much larger than the range of the potential. So we don't need to worry about that. The potential is very small compared to the box. But we're going to send in some initial plane wave k initial like this. This is our initial state. And the final state, let's call it k, like this without any subscripts. So this is initial and final. If we compare this to the general formalism I gave you for time-dependent perturbation theory, this is like the initial state is like what we called I previously, and the final state is what we called n. We use the symbol n for a variable final state in the general formalism of the Dyson series. Here we need to identify this with wave vector k. Likewise, I is identified with k sub I. This means that omega ni, which is equal to en over minus ei over h bar, goes over into h bar over 2m times k squared minus ki squared. This is just a sequence of changes of notation for this problem to adapt the general formalism to this problem. And the omega ni must be understood to be equal to this for the applications of this problem. All right. The states of the system are parameterized by the discrete k vectors. So we can visualize them as constituting a lattice of points in k space. So if I draw k space, for example, kx and ky, then there's a square lattice of points here, like so, representing the states of the system. And the separation between these, the lattice spacing between these, is given by 2 pi over L, just by solving for the periodic boundary conditions. And what that means is the density of states in k space. By that I mean if I take some volume of k space and ask for how many points there are in that volume per k volume, that's equal to the reciprocal of this cubed. It's L over 2 pi quantity cubed, which is therefore equal to the volume of the box in real space divided by 2 pi cubed. All right. So those are some features about the lattice points in k space. All right. Now then, let's talk about what we want to do. Our formulas allow us to find the probability, what we previously called Pn of t. Let's now replace this by P sub k of t. This will be the probability for the system to be in plane wave state k as a function of time. We're mainly going to be interested in the case where k is not equal to k initial. That kills the Kronecker delta in the Dyson series. But it also means that we're really talking about scattering, because if the system stays in the initial state, then there was no scattering. You need these two to be different in order to talk about scattering at all. So that's the case that we want. Now then, here, let's set this up in the following way. Let me go back to a diagram of space x, y, and z like this. We got our potential down here. Let's say we've got some detector out at some position here. I'll call it D, like so. Let's draw a unit vector. I'll call it n hat f final, which is in the direction of the detector. I didn't draw this very well, but let's make that drawing. So n hat f is the direction of the detector. Of course, the f just means final, and n hat's a unit vector. Now, meanwhile, in k space, where the lattice is, kx, ky, and kz, let me draw in a vector. Let me draw in again a vector n hat f, like so. Let me draw the vector. I'm going to omit the lattice points in here, but imagine this being filled up with lattice points. Let's define. Let's make a definition. Let's define a vector I'll call k final, which is equal to n hat final multiplied by the magnitude of the initial k vector. You can define anything you want, and you'll see in a minute why I made this definition, but allow me just to make this definition. What that means is that there's a k vector final in k space, which is in the direction of the n hat f, and its magnitude is the same as the magnitude of the incident k vector. That means that k final has the same energy, represents the same energy as the incident particles. let's also draw a cone, small cone, a solid angle delta omega around the direction of K final. Now then, we can imagine, since K space is filled with lattice points, we can imagine that there are some lattice points inside the cone and some that are not. If I have this P sub K of T, the transition probability to be in a certain final K state as a function of time, we can study what happens to that. We can calculate it. But it turns out this is not such an interesting quantity, because in the limit that the volume of the box goes to infinity, this sort of loses meaning. It actually goes to zero. It's not so interesting to look at a single K value. Instead, what we want to do is to sum over K values to get the interesting probabilities. And what K values do we sum over? Well, an interesting choice is to sum over K values that are inside the cone, like so. Because if we do that, then what we've got is a probability that the outgoing wave, the scattered wave, in effect is moving in a K direction, which is inside the cone. And if that's the same cone that's subtended by the solid angle, by the same cone of a solid angle that's subtended by the detector in real space, and this can be translated into the counting rate as seen by the detector. All right. So this is the transition probability to be inside the cone. Now, in some circumstances, the transition probability is proportional to time. And so if we divide by time, we get a transition rate. So allow me to do that, divide by time, and let's call this W then, which is this then becomes the transition rate to make transitions into the cone. The transition rate is related to the cross section in the following way. It's by the incident flux. The cross section is nothing but the transition rate normalized by the incident flux. This formula that I'm writing here is essentially the definition of the cross section. We can relate then the cross section to this sum over transition probabilities. Dividing by J incident will do it for us. We shouldn't really call this this transition. Allow me to change the notation. This W is the transition rate to end up inside the cone. Let me replace it by the following expression: dW d omega times delta omega, where dW d omega is the transition rate per unit solid angle, and delta omega is the small solid angle of the cone. Likewise, for sigma, we'll replace this by d sigma d omega times the corresponding solid angle delta omega, like so. All right. And if we do this, we can now then solve for the d sigma d omega. And this gives us the differential cross section d sigma d omega is equal to 1 over delta omega, 1 over J incident, 1 over time, the sum on K inside the cone of the transition probability P sub K of T. All right. And what I'd like to do in the next 10 minutes, which is all that's left tonight, is to try to work this out and to get an actual expression for it. Let's work from left to right and take one piece at a time. What is the incident flux? The incident flux is the incident number density times the incident velocity. That's the definition of the flux of particles. We have just one particle. We just have one particle in our volume V, so N incident is 1 over V. As far as V incident is concerned, that's the K incident, Ki, times H bar, which is the incident momentum divided by the mass. This is just a way of converting a wave vector K into a velocity. That's all we've done here. So anyway, that takes care of the J incident. Now, what about the sum on K in the cone? We're going to be interested in the limit at which the volume goes to infinity. And when we do, the density of points in K space goes to infinity. So this can be replaced by the density of states, which is volume over 2 pi cubed in K space, times an integral over the cone, d cubed K. And the integral over the cone d cubed K, because the cone is just a small solid angle, I bring it down, it's just a small solid angle. In principle, it's an infinitesimal solid angle. This turns into just the solid angle delta omega times the integral from 0 to infinity of K squared dk. if you like, I transform this d cubed k into spherical coordinates in k space. The angular integral just gives you delta omega, which is easy, and what's left over is the radial part of the integral. All right, so we have that. So that then takes us up to the sum on k of k in the cone. Now, what about the transition probability? Let's work on that. So the formula in the general notation, to remind you, was that Pn of t was equal to 2 pi t over h bar squared times this sine squared omega t over 2 over omega squared times the square of the matrix element. But this thing here, we decided we were going to write this as pi over 2. I'm sorry, I did this wrong. I did this wrong. There's no t here. This was a 4 over h bar squared. Get that formula right. This we decided we're going to write as pi over 2 times delta t over omega, and this we keep the same. So the Pn of t then, in a different expression, becomes 2 pi. This is pi over 2t. 2 pi t over h bar squared times delta sub t of omega times the square of the matrix element. Okay? Now, the delta sub t of omega is eventually going to turn into a Dirac delta function because we're going to let t goes to infinity. I'll say more about what that limit involves in a minute, but this is what we're going to do. And the omega itself, as I explained to you, is the omega itself, let me write this way. The omega itself, as I explained, is given by h bar over 2m times k final squared minus k initial squared. You can see that the omega goes to 0 when k final equals k initial. That's, of course, energy conservation. And so delta of omega can be written this way as delta of k minus k initial using the rules for delta functions divided by d omega dk. Really should put an absolute value on that. But d omega dk, we just calculate it, and we get h bar k over m, like so. In fact, you can see that's a velocity. So this becomes delta of k minus k initial divided by h bar k over m in the denominator. So that takes care of the capital delta of t in the limit where t goes to infinity. Now, what about the matrix elements? The state I goes over into the state ki, and the state n goes over into the state k, changing the notation we need to change. So the matrix element we want is k on the left. The H1 is the potential U of R, and then the K initial is on the right, which if we translate this into an integral using our normalized wave functions, this becomes 1 over the volume of the box times the integral over the volume of the box, d cubed R, times e to the minus I k dot R times U of R times e to the I k initial dot R on the right-hand side. And you can see that this becomes proportional to the Fourier transform of the potential. This is just the matrix elements of the potential between initial and final plane waves. Allow me to define the Fourier transform of the potential. I'll call it tilde to indicate a Fourier transform, and I'll let the variable upon which the Fourier transform depend. Let's call that Q. This is a definition. Let's define this as the integral over R divided by 2 pi 3 halves times e to the minus iq dot R times U of R vector. This is just the usual Fourier transform, except that I've used a convention of normalization that balances the factors of 2 pi. It's just a matter of preference to do it that way, but I have to say what my convention is, and so allow me to use this convention for the Fourier transform. Now, if we do this, then this integral here, which is the same as the matrix element, turns into 2 pi to the 3 halves divided by the volume V times U tilde of K minus K initial. So we see that the matrix element, which appears in the first order perturbation theory, time-dependent perturbation theory, becomes proportional to Fourier transform of the potential evaluated at k minus ki. If I think of k initial as being, some direction like that for the incoming plane wave, then the k is the scattered wave, points off in some direction like that, and the angle between them, let's call it theta, is a scattering angle. Also, k minus ki is the final momentum minus the initial, well, if you multiply by h bar, it turns into the final momentum minus the initial momentum. So k minus, or let's put it this way, h bar times k minus ki is the momentum transfer in the scattering process. And what this means is that when the smoke clears and we get the cross section, you'll find that it depends only on the momentum transfer. This is characteristic of first order time dependent perturbation theory. I'm jumping ahead to say that, but this is where it comes in. All right. In relativistic problems, by the way, you find it's proportional to the form momentum transfer. I mean, this is related to the invariant expressions for cross sections and relativistic scattering. Okay, now, I think I've got together all the details that we need now to assemble everything, but the pieces are scattered. So let's see if I have time to do it. So go back here. Let's do this. I've got d sigma d omega equals 1 over delta omega, 1 over J incident. J incident is here, so it's V times the mass m divided by h bar k sub I. Then 1 over t time t. Then the sum on the cone turns into down here turns into the volume over 2 pi cubed. The times delta omega. I'm following this line down here, times the integral from 0 to infinity of k squared dk. That takes care of everything up through the sum, and now I need the pk of t. So switching over to the next page here, the pk of t turned into a translation of these factors. Get these pages out of the way. pk of t turned into a translation from this notation here, the general notation, into our specific problem, which is outlined down below. So I have, first of all, a 2 pi t over h bar squared. I have the capital delta t of omega, which is going to turn into a Dirac delta function. So that turns into a delta of k minus k initial. This is multiplied times this, divided by this denominator, which is h bar k, divided by mass m. Then what's left over is the square of the matrix element. We work that out down here. Here's the matrix element not squared. So now I'll square that. We get 2 pi cubed divided by volume squared. We get the square of u tilde of k vector minus k initial vector, absolute value squared like so. So putting all the pieces together, we get this rather long and complicated looking formula here. Now there's a bunch of limits we're taking here. We're taking the limit as time goes to infinity. I'll explain what that means in more detail, not tonight, but tomorrow night or next lecture. We're taking the limit, the volume goes to infinity. We want delta omega to be small. And so those things ought to go away. And indeed, you can see they do. The volume factors, for example, here's a volume upstairs, and 2 downstairs. So they cancel. The time here, there's a time here and a time there, and that goes away. They cancel. That means that we had a genuine transition rate, you see. We have delta omega and a delta omega, they cancel. On top of that, there's factors of 2 pi that cancel, like so. As far as the integral goes, you see it's an integral only in the magnitude of the final vector k. What that means is that we're integrating over the outgoing cone of the final wave, the magnitude of the final wave vector k, summing over all the states that are inside that cone. Notice that we're not just setting the final k vector equal to the initial one and demanding conservation of energy. No, what we're doing is we're summing over all the states that lie in the cone, including the ones that conserve energy and the ones that don't. The ones that conserve energy are just at one fixed value, the magnitude of k. as to say on a sphere that cuts through this cone. But we sum over all of them, and that's what this integral does. However, the delta function, which appears here, which came from taking the limit as t goes to infinity, is going to mean that on doing the integral, we only need to evaluate at k equals ki. If t is not really infinity, but just large, then this delta function has some width in k space. And that's a way of saying that if we do this over a finite time, then there's some uncertainty in the energies, and we're actually integrating over, the final energy is not fixed, but we're integrating over all the states, including those that don't exactly conserve energy. That's what that means. And this delta function here is an idealization of that process where the t goes to infinity. Well, in any case, this now makes the radial integral easy to do. So you just then need to do this and clean it up. And if you do, here's what you find. You get d sigma d omega is equal to it's 2 pi times the square of the mass divided by h bar to the fourth times the square of the matrix element u tilde evaluated at k vector minus k initial vector absolute value squared. And this is the main result then for this scattering problem. This is the cross section derived by first order time dependent perturbation theory. I have just one more very quick comment. The k that appears here is a vector, but we integrate it over the magnitude of k, not the vector k. So what does this k vector mean? What it means is that inside this cone, since the solid angle is small, it means that k vector is actually equal to the magnitude of k times n hat final, which was the direction of the cone. And so when we do the integration here, then the magnitude of k is set equal to k initial, which amounts to conservation of energy. And it means that magnitude k then gets replaced by k initial. So that goes into k initial times n hat final. But that was our definition of what we called k final. So if I can put a final on here like this, you see k final. This then explains the cross section here and the vectorial nature of that dependence on the Fourier transform of the potential. This result is the same result we get in what's called the first Born approximation. We'll say something about that later. Effectively, one has derived here, I have derived here for you tonight, the first Born approximation by means of time-dependent perturbation theory. Okay, I'm sorry I ran over. Are there any questions about that? That's all for tonight. Are there any questions about that? Yes, a question. I thought there was a question. You have probably seen this calculation before. It's normally covered in undergraduate courses, but it's built in as an application of the Fermi-Golden rule. And you may notice I didn't use that. The Fermi-Golden rule is certainly simpler than what I did, but it doesn't apply in all circumstances. And it's also kind of cookbookish. And I personally don't like it. And so even though writing all this out is rather complicated, the individual steps, all of them make sense. What you're doing is you're summing over probabilities. They grow in proportion to time. You divide by time to get a rate. You normalize by flux to get a cross section. And so the sequence of the logical sequence is clear, even if the algebra is complicated. And for that reason, I prefer it this way. And I won't be talking about Fermi-Golden rules. All right. All right, if there's no other question, one more chance for questions. If not,
yeah, I had a quick question.
Yeah, sure.
Just to clarify, what is d sigma d omega again? What does it physically represent?
It's a differential cross section, and I didn't review what that means because I assume that you've seen them before. But there are notes in the notes that I for my course. I actually explain what that is. You can see a definition of it and the details of that in the notes. If you have any further questions about it, feel free to ask me. By the way, it's something you'll for sure want to know, before taking prelims somewhere, because they'll be asking questions about that.
All right, cool. Thank you.
Maybe you passed your prelims already, but anyway, this is basic stuff. You should know it. So feel free to ask me about it if you have any questions. All right, any other questions? All right, if not, I shall stop screen share. I shall stop recording.